Hello students, welcome to EPG Pathshala. I am Dr. Rajiv Jain from Jivaji University Gwalior. Today we are going to discuss some fundamentals involving gas and high performance liquid chromatography in chromatography part 2 under the paper Fundamentals of Analytical Chemistry. Learning objectives of today's lecture is that, as you know, there are two phases in chromatography. One is the stationary phase and another is the mobile phase. When mobile phase is liquid, then its flow on the solid surface is slow and it is time consuming. When that mobile phase is gas, then it is very fast and this separation takes place in less time. When liquid flows over the solid, in case of solid stationary phase, it takes time due to the adsorption is taking place at every particle of the surface, because the particles of solid on the surface, their characteristics are different in comparison to the inner particles present there. In case of liquid chromatography, when the liquid is a fine layer of liquid is present, is fixed over solid support, then separation takes place between two phases and both phases are liquid. One is moving and one is stationary, and here partition is occurring. We may call it as different plates and it is taking place, partition is taking place, and you may compare it, you may very well understand it, compare it with fractional distillation. When different components are separating by heating in fractional collector, we fractional distillation is occurring. Similarly, here behavior is taking place by liquid partition is taking place, and this type of chromatography is called as liquid partition coefficient based upon their different distribution in or distribution coefficient. Another type of chromatography is gas liquid chromatography, then gas solid chromatography or liquid solid chromatography. And another type of chromatography may be ion exchange chromatography. But here in this lecture, I shall discuss, we shall try to understand liquid chromatography by taking the example of high performance liquid chromatography, and another is gas liquid chromatography by taking the examples of gas liquid chromatography, and both the techniques we shall learn here in today's lecture. Liquid partition chromatography. Partition chromatography offers great advantages over adsorption chromatography. It is far more reproducible and predictable from solubility data. Even more important, the distribution coefficient is constant over a greater range of concentration, yielding sharper, more symmetrically shaped bands. The more polar of the two is normally coated on a solid support. Optimally, the fraction of a solute which is dissolved in the mobile phase should be in the range from 0.05 to 0.5, otherwise the retention time will be too long or too short. There are some situations in partition chromatography in which it is advantageous to use the non-polar organic solvent as the stationary phase in order to get a more favorable value for partition coefficient. Such type of chromatography are known as reverse phase chromatography. Obviously, a non-polar solid support is required. Powdered rubber coated with benzene is a very satisfactory stationary phase with an aqueous mobile phase. High performance liquid chromatography. This apparently simple expedient, combined with a number of other improvements in apparatus and technique, has evolved into a new practice of liquid chromatography, which is competitive with gas chromatography in speed and resolution of complex mixtures. Like other types of chromatography, in this chromatography also has two phases, stationary phase and mobile phase. A stationary phase is supported on a solid support. So in this case, closely sized particles as small as 10 ftm are now becoming available. Particles smaller than 10 ftm are extremely difficult to handle and give almost an impermeable column. To alleviate this problem, a solid glass bead of 30 to 50 ftm in diameter can be coated with a layer of porous material. These coated beads are called pellicular beads. The porous layer may serve as a stationary phase or be coated with a very thin layer of liquid stationary phase with an extremely large surface area. The thin film of stationary phase may be wrenched away by mobile phase under the high pressures used. Porous silica beads are esterified with various alcohols, forming the corresponding silicate ester. The organic parts stand on end, projecting from the bead surface and resemble a brush, a name used to describe this type of packing. These esterified siliceous packings are not thermally stable and are subject to hydrolyze and exchange with lower alcohol. Another type of chemically bonded packing utilizes silicon polymers, which are more stable because of their three-dimensional cross-linked structure. Column packed with small particles require high inlet pressures in order to give a reasonable flow rate. Pressures up to 10,000 psi are not difficult to handle in the small columns used. Improved pulse-free pumping systems are incorporated in modern liquid chromatographs detectors. The smaller columns and fast flow rates place rigid requirements on the detection system. Flow through detectors with low dead volumes and high sensitivity are a necessity. Two types of detectors are currently popular. One is based on a flow through microcell placed in an ultraviolet spectrophotometer. A low pressure mercury lamp is commonly used as a source and the absorption measured with the 254 nanometer line where most organic compounds having double bonds or aromatic groups cause at least some absorption. Since most common solvents do not absorb radiation in the ultraviolet and visible region, these detectors are extremely sensitive and free from interference. A second popular detector, the differential refractometer, continuously monitors the difference in diffractive index between the pure mobile phase and the column effluent. These devices respond to essentially all sample components, but the refractive index differences are minute and fluctuate with small changes in temperature or composition of the mobile phase. Another detector utilizes the flame ionization detector developed for gas chromatography. A continuous wire or fine chain moves through the stream emerging from the column outlet where it becomes coated with a film of the effluent. The wire then passes through an oven to evaporate the mobile phase and finally through an oxidation oven in which the components are burned in a stream of oxygen at about 850 degrees centigrade. The gaseous products are passed over a nickel catalyst bed at 350 degrees centigrade, which converts the carbon dioxide to methane, a substance that is readily measured by the flame ionization detector. A typical high performance liquid chromatograph is shown in figure 1. In this figure, five components has been resolved by a single experiment. To identify components 1, 2, 3, 4, 5 has been shown separately here and they are resolved and could be identified and separation is very clear as can be seen from the figure 1. Unlike other chromatographic techniques, gas liquid chromatography is a closed system. Here, columns remains in a oven which is maintained at a particular temperature. The sample is introduced into that column through a self-sealing silicon septum with the help of a micro syringe. Sample is taken in a solution by with the help of a micro syringe. The solution is injected in through a self-sealing silicon septum into the column, and that column is placed into a that column is placed in a closed oven which is maintained at a temperature. As soon as sample is introduced into the column, it vaporizes, and along with carrier gas, it is introduced into the column and it moves over the already present there liquid supported over a solid. That is why it is gas liquid chromatography. Why it is gas liquid chromatography? Because here separation is taking place between mobile phase, which is a gas, and stationary phase, which is a liquid. As you can see from figure 4, which is very clear here, the column is placed in a fixed temperature in an oven, and as soon as the sample is injected into the column, it vaporizes, and then along with gas it moves over a liquid, and due to the interaction between them, due to the difference in the partition coefficient of different components, then separation takes place, and then it goes to the detector, and by using different types of detectors, samples are identified. As is clear from the figure that the first thing is gas chromatography is the carrier gas. At ordinary pressures and temperature, common carrier gases which are chemically inert, for example helium, nitrogen, hydrogen and argon, are used. These gases are relatively inexpensive, readily available, and are not hazardous to handle other than the flammability of hydrogen, which does require adequate safety precautions. Also, because they are inert, interactions between sample molecules and carrier molecules can be neglected, and the distribution coefficient of a component is determined entirely by its volatility from the stationary phase. For most purposes, helium is the popular choice. Passage through a cold molecular sieve trap is very effective in removing the last traces of water vapor frequently found in commercial gases. Flow through the column is caused by the difference in pressure between inlet and outlet. Pressure regulating valves maintain an inlet pressure pi of 10 to 50 psi or occasionally higher. The outlet pressure P0 is normally atmospheric pressure, although it can be increased by restricting the outlet orifice. On some instruments, flow controllers automatically vary PI to maintain a constant flow rate, but on most instruments, it is assumed that a constant PI is adequate. In contrast to liquids, gases are compressible, and this leads to complications in determining the flow rate and volume of gas passing through the column. In gas chromatography, after carrier gas is how to introduce the sample into the column. As in other types of chromatography, it is important to introduce the sample in the shortest time and in the smallest volume possible. It is also true for gas chromatography. The sample chamber may be heated for rapid vaporization of liquid samples and should be designed so that the carrier gas sweeps the sample directly into the column. If these requirements are not met, the sample will be unnecessarily spread out before the separation process has begun. In some instruments, the sample is injected directly into the column at the inlet. This is preferable for most samples unless they have a very high boiling point. The size of the sample is dictated by several factors, the amount available, the capacity of the column, and the sensitivity of the detector. The ordinary laboratory chromatograph can handle liquid samples in the range of 0.1 to 10 microliter and gaseous samples in the range from 1 to 10 ml. Capillary column requires much smaller samples of the order of 10 raised to power minus 3 to 10 raised to power minus 2 microliters. Samples of this size must be introduced by a splitting technique as shown in the following figure. In this way, only a small fraction of the sample is injected, the remainder is vented to the atmosphere. Accurate measurement of the sample of this size is questionable and may account for much of the error in quantitative analysis. For reliable thermodynamic data, retention values should be obtained with several sample sizes and extrapolated to zero sample. Liquid samples are injected from a microsyringe of appropriate capacity through a rubber septum. A swift, neat motion of the plunger is necessary. Gas samples are easier to measure accurately because of their larger volume. For routine analysis, a two-position hex port valve shown in following figure is convenient and accurate. Solid samples can be dissolved in a solvent or sealed in a thin-walled glass vial, which is then inserted into the sample chamber and finally crushed from the outside. Next part, or very important part of the gas chromatograph, as in the other types of chromatography, are the columns. There are two distinct types of columns in common use: packed column and open tubular, that is, capillary columns. The packed columns are easier to fabricate, less expensive, last longer, have a higher capacity, and suffice for all but the most difficult separations. The capillary columns have less pressure drop and therefore can be made much longer. Bed columns are usually 1 to 20 meter long and 3 to 10 millimeter in diameter, although columns up to 10 centimeter more in diameter are used for preparative scale work, whereas capillary columns are usually 10 to 50 meter long and zero point 0.2 to 1.2 millimeter in diameter. Geometrical configuration of the column is of little concern as long as the bends are not sharp. Columns are bent in a U or W shape or coiled to fit the oven. Short columns are often made of glass, but longer columns are made up of copper, aluminium, or stainless steel tubing to facilitate bending, which may be done after the column is filled. It is possible to draw glass capillary tubing in lengths of several hundred meters. Capillary columns up to a mile in length have been fabricated. Next thing is solid support on which liquid is to be coated. The ideal solid support should have a high specific surface and the surface must be chemically inert, although wettable by the liquid phase, so that the latter will spread in a thin layer of uniform thickness. In addition, the solid support must have thermal stability, mechanical strength, and be available in uniformly sized, near spherically shaped particles. The most commonly used supports are derived from diatomaceous earth, a spongy siliceous material consisting of the skeletal residues of diatoms, a form of microscopic algae. The raw material has a surface area of about 20 meter square per gram, but it is very fragile and of course loaded with impurities. In one process, the diatomaceous earth is mixed with clay and baked at 900 degrees centigrade. It is then crushed and graded according to size. The final material has a surface area of about 4 meter square per gram. The surface is fairly active toward polar compound and is pink, hence designations like chromosome P. In a second process, the raw material is mixed with a solution with a sodium carbonate flux before baking. The product is more fragile, less chemically active, has a smaller surface area, that is 0.5 to 1 meter square per gram, and is wide, hence designations like chromosome W. These support materials are interlaced with a network of fine pores requiring about 0.5 by weight of a liquid to cover the entire surface with a monolayer. As a heavier coating is applied, the finer pores fill up first, but even with a 20% coating, many free passageways still exist and the average thickness of the layer is still only a few hundred angstroms. The surface of commercial fabric chromosome B has the general structure as shown below. The OH groups are acidic and somewhat polar and tend to react with polar solutes, especially those with basic functional groups. The surface activity can be partially reduced and some impurities removed by washing in acids or bases. For the separation of amines, it is desirable to leave a thin coating of sodium hydroxide on the surface. A very effective treatment consists of selenizing the surface with hexamethyl disilazane as shown in the following figure. In this figure, polar OH is replaced by a relatively inert trimethylsilyl group. Powdered Teflon is useful as a support for very polar solutes, but it has a low surface area. It is so inert that it is difficult to coat evenly. It is more easily handled if first cooled in a refrigerator. Some other supports which have been suggested are microglass beads, graphite carbon, and carborundum, etc. In gas liquid chromatography, two phases are stationary phase is liquid phase, and this liquid phase is supported on a solid surface, and other mobile phase is a gas. So we have chances of manipulations or taking thousands of different types of liquid phases are available, but mobile phase is usually a gas. So by taking suitable liquid phase, which liquid phase should be suitable? It should have a it should not react with the components of the substance which we are separating. Means it should be unreactive to the components of the mixture which we are separating. As in the case of gas liquid chromatography, we vaporize the components. So at that temperature, that liquid phase, um, the solvent which we are taking as a liquid phase should not boil. It should remain unreactive and in the natural physical form at that temperature. This is the characteristic of that. Another characteristic of that liquid phase is that its behavior should not change with the temperature. It should be stable at different places of the column. When it is moving from inlet to outlet, its chemical and physical nature should not change. And here, when separation is taking place, then theoretically different types of interactions are possible. So interaction, mobile phase, uh, your components which you are separating are present in the mobile phase in gaseous state, and they are moving on the stationary liquid phase. So different types of interactions are possible. Suppose dipole-dipole interactions are possible. Hydrogen bonding may form. Certain types of diffusion may take place. So by that, differences in their partition coefficient arises, and due to that differences, separation takes place at different levels. So the component which is uh, which is more strongly held comes out at the last, and which is loosely held or which comes out first. Here interaction chelate formation may also take place. So different types of interactions are possible, and that is the basis for the separation of different components of the mixture. The last part of the experiment which is to be performed is the identification of the separated components, and this is done with the help of detectors. Separations performed in the column must somehow be sent and recorded, and this is done with the help of detectors. All of the components are highly diluted in the carrier gas with concentrations of 1 ppt at best ranging down to 0. Furthermore, sharp peaks may pass through the detectors in less than a second, while the last peak may not emerge for hours and be barely discernible above the baseline. Somehow, the detector must ignore the large amount of carrier gas and find the trace amounts of sample components contained therein. The universal detector has not yet been invented, for it must meet all of the following requirements, that is, low limit of detection, linear response over an extreme range of concentrations, uniform response to all possible substances, simple calibration, short response time, small internal volume, low noise, long term stability, and it must be simple, inexpensive, robust, and safe to operate. There may be some occasions when selective response to a few components is desirable as an aid to identification or a means of finding a trace component which is incompletely separated from a major component. For this purpose, different types of detectors have been developed. Differential detectors measure instantaneous concentration or instantaneous rate of emergence of the component. Integral detectors accumulate the instantaneous signal and give the total amount which has been measured up to a given instant. Signals from differential detectors are usually integrated for quantitative analysis, and signals from integral detectors are often differentiated to make them easier to interpret for qualitative analysis. Either signal, as shown in following figure, can be derived from the other. Detectors can also be classified as destructive or non-destructive, depending on whether or not the sample components can be collected unchanged for further study. Hydrogen flame detector. One of the simplest detectors is the hydrogen flame detector shown in the following figure with an extremely simple chromatograph. Hydrogen must be used as a, in this detector, hydrogen must be used as a carrier gas. It is burned as it emerges from the column through a hollow needle, yielding a nearly colorless flame. When an organic component emerges, the flame becomes yellow. Retention time can be measured with a stopwatch. The amount of the component is roughly proportional to the height or luminosity of the flame. This may sound very crude, yet it is not difficult to install a thermocouple to measure the flame temperature or a photocell to measure the luminosity and increase the accuracy manifold. Better still, since most organic compounds are ionized in the flame, an ion current can be collected between two oppositely charged electrodes as shown in the following figure. This is the principle of the flame ionization detector, one of the most sensitive and popular detectors in current use. The ions produced are collected between two electrodes, one of which may be the jet itself. Because of the electrical resistance of the flame is very high and the current is extremely small, the associated electronics are complicated and moderately readable. The response depends also on the state of oxidation of the carbon atoms. Those which are already completely oxidized do not lead to the ion formation. The detector is insensitive to most inorganic compounds. It is especially worth noting that it does not see water vapor or air. The flame ionization detector is relatively simple, extremely sensitive, and has a wide range of linear response. Next type of detector is thermal conductivity detector. The measurement of the thermal conductivity of a gas is based on the transfer of heat from a hot filament to a cooler surface. Thus, the gas conducts heat from the filament to the wall. If a constant amount of electric energy is supplied to the filament, its temperature will be a function of the thermal conductivity of the gas. Rather than determining the temperature of the filament, it is easier to determine its electrical resistance, which increases with temperature. As applied to gas chromatography, a dual detector is used to minimize the effect of the thermal conductivity of the carrier gas and to minimize the fluctuations in the temperature, pressure, and power supply. A schematic diagram of this type of detector is shown in the following figure, and the associated electrical circuit is also shown here. In some detectors, thermistors are used in place of filaments. Thermistors are somewhat more sensitive than filaments below 100 degrees centigrade, but reverse is true above 150 degrees centigrade. The temperature of the filament is a function of the bridge current, the geometry of the cell, and the thermal conductivity and flow rate of the gas. Increasing the bridge current will increase the running temperature of the filament and increase the sensitivity, but the filament will burn out sooner. Since the detector is measuring thermal conductivity, it is very important to keep the temperature of the detector walls constant. Often, this is the limiting factor for quantitative analysis. The thermal conductivity of a mixture of gases is not easy to calculate, and this detector must be calibrated for each compound for higher accuracy. The thermal conductivity detector is simple, rugged, inexpensive, moderate sensitive, non-selective, especially non-destructive, very accurate if properly calibrated, and more widely used than any other type of detector. Another detector which is used in electron capture detector. In this detector, the effluent gas is ionized by a stream of particles emanating from a radioactive source. Thus, the carrier gas produces a steady supply of positive ions and free electrons, which can be measured as a standing current between two charged electrons, much like the hydrogen flame detector. When sample components pass through the detector, the standing current may be perturbed. Compounds containing highly electronegative atoms capture free electrons very efficiently, and they are detected by the decrease in the standing current. This occurs because of the increased rate of recombination of positive and negative ions compared with positive ions and electrons. Other species have little effect on the ion current. Thus, the electron capture detector is highly selective and very sensitive for compounds containing halogens, phosphorus, lead, nitro groups, and polynuclear aromatic ring system. It is ideally suited to the detection of minute traces of many pesticides and defoliants. Other types of detector which may be used are, are coulometric titrator, in which the column effluent is burned to give HCl, H2S gas, and then pass through a solution to be titrated with electrolytically generated silver ion. In many cases, flow photometer detector, in which the flame of an FID serves radiation source of a flame photometer, has also been used. Students, as you have seen here, we discussed liquid-liquid chromatography, and we took two types of chromatography here, gas-liquid chromatography, and another is the liquid-liquid chromatography. One of the limitations of gas chromatography is that only those substances can be separated which are volatile at a temperature, at a given temperature, or in experimental conditions which are volatile, only that components can be separated. But the advantage is that separation is very fast, very fast. So in, in a within a very short time, number of components of a mixture can be separated. So this is the limitations here. But in liquid-liquid chromatography, as you have seen in the case of high-performance liquid chromatography, the separation is slow because liquid is flowing upon another liquid, and it takes some time. And as you have seen their graph in plots, you can see there is a difference in both the plot in Detector equation, Detector plots, that here separation is slow. But another advantage of liquid-liquid chromatography is here that the chances of manipulations here are very high, combination manipulations, because in both the phases, in liquid phase, mobile phase, as well as in stationary phase, you can take hundred thousands of different types of stationary phase and mobile phase. Whereas in gas liquid chromatography, you have only in hand the chances to change only the stationary phase, but mobile phase is gas, which remains almost the same. So if we compare both, but here the stability of the liquid, stability of the mobile is very important in your gas liquid chromatography. The liquid, such type of solvent should be selected which is stable at the temperature at which your components of the mixture vaporize or are volatile. The nature of the solvent should not change. And the another advantage of liquid-liquid chromatography, as you have seen in case of high performance liquid chromatography, is that here we can study the substances which are thermally not stable. Many substances like your proteins, different types of proteins, body fluids, which are not thermally stable, we cannot heat them. They can be easily separated by high performance liquid chromatography, but they cannot be separated by gas liquid chromatography because at high temperature, proteins will coagulate, their nature will change, nature of body fluids will change, they are not thermally stable. So, it is the high performance liquid chromatography in that case is superior to gas liquid chromatography. So we can compare both types of chromatography, and but the principle remain almost the same, that separation is taking place by partition difference in partition coefficient of the different components of a mixture. Thank you.